Let's take a look at the next part of our chemical bonding unit in Chem 20. So what we are doing in this lesson is looking at something called Lewis structures. Now it will take a little bit of application of our knowledge of our previous lesson on bonding theory, so you should be pretty fresh on that content. Another thing is that when we get towards the end of this lesson, we are going to be applying some knowledge on molecular compounds. And some of this might not make full sense until we get through our lesson on explaining molecular compounds. The theory behind it all is quite basic, and you'll be just even more certain on the content once we get through a few more lessons here. So, our Lewis structures. Let's begin discussing what Lewis structures are and how to determine these structures. So, for Lewis formulas, we have Lewis formulas for our elements. Now, a Lewis symbol is a helpful tool, and it essentially describes how atoms bond. Again, this is all we're talking about is bonding, and because we talk about bonding, we are obviously going to be talking about electrons, which is very important. So to draw a Lewis symbol, we start by writing the element symbol, and that symbol represents the nucleus and all the filled electron shells. Okay, the dots around our nucleus or our element symbol represents the valence electrons. So our dots represent our valence electrons. And we start by placing valence electrons singly into each of the 4 valence orbitals. Okay, so again, they like to spread out. Our electrons like to spread out first, and then we can pair them up as the orbitals start to become full. So again, we represent our electrons with dots. Everything that's in the nucleus or filled electron shells is represented by the symbol, so we're only looking at valence electrons, which is important because we only look at valence electrons when it comes to bonding. So if we take a look at some examples here, if we look at carbon, all right, so if we look at carbon, I know that carbon has, and let's just jump over, I'll show you how I know this, but I know that carbon has 4 valence electrons. Now let's make this so I can see it, okay? Okay, here we go. So when I go to look at carbon, I see that carbon is in the 14th column. And because carbon is in the 14th column, I know that it has 4 valence electrons. Now, if I'm not sure, I can also count where the element exists on the periodic table if I count from the left to the right. So if I start with lithium, that's 1, 2, 3, 4. That means there's 4 electrons in that valence shell. That's just simply looking at where the element exists on the periodic table, starting from the left of that row and counting in towards the element wherever it might exist, and that will give you the number of valence electrons that we have. So carbon has, and I'm just gonna switch this here. Oops, that's not what I want. There we go. So carbon has 4 valence electrons. So again, I'm gonna represent those valence electrons by dots. Now, remember that this C represents all of the filled orbitals, which is that first column or the first row of our periodic table, which has 2 electrons in it. But then I also know that carbon is in the second row of the periodic table, meaning that it has 2 energy levels, which also means that in my second energy level is my valence shell or my valence energy level. Now, because I start by placing my 4 electrons in each orbital, now essentially I have to envision this carbon as being inside a rectangle or a box, and that will help me to understand that each side of our element represents an orbital. So because there's only 4 electrons, I start anywhere and I go either counterclockwise or clockwise, and I indicate that there's 1 electron in each one of those orbitals, but that is it. There's only 4 electrons to place, and there's 1 electron in each orbital. If I take a look at oxygen, I know, and remember that this oxygen again, we pretend that it has 4 sides of a square or a rectangle around it representing an orbital. And when I jump back over to my data booklet, I see that oxygen is in the 16th column, which means that it has 6 valence electrons in it. So again, if I count from left to right, 1, 2, 3, 4, 5, 6 electrons in that valence shell. So again, I start by drawing out my 1. I'm just going to change the color here. 1, 2, 3, 4. And now that the electrons have all been spaced out, I'm going to then add another electron, 5, 6. Because I need to have 6 total electrons in my valence shell, I start by spreading them out evenly, and then I go back and I add 1 and add 1. Now, I always go in clockwise or counterclockwise direction so that my valence electrons are all sort of in order like this. I do not want to skip across and put 1 electron at the top of the O and 1 at the bottom of the O. I want them to be filled in order. So that is scientifically what happens. They do not jump electron energy levels. So we make sure that we put them in that order. Okay, if I take a look at phosphorus, again here we look at phosphorus. We picture this having a box around it, and I take a look at my data booklet and I see that phosphorus has 5, so I go 1, 2, 3, 4, and 5, meaning that I have 5 valence electrons in my valence shell, or my outer energy level. Okay, so this is how you draw Lewis formulas for elements. You simply indicate the electrons and where those electrons exist on that element, or in those orbitals, I should say. Now, Lewis structures and Lewis formulas can also be applied to a molecular compound. Okay, and molecular compounds, remember, they're compounds that have electrons that are being shared. So that's very, very important. Molecular compounds have what we call of covalent bonds, or bonds where we share electrons. So Lewis structures allow us to predict an entity, structure, polarity, and shape of a molecule. And there's 5 main steps to predicting Lewis structures that we're going to go through right now. And I strongly recommend you write these 5 steps down as a reference as you go through some assignments, and so that you get practiced up for any sort of unit exam. So the central atom is the atom to which all other atoms bond. Okay, all the other atoms that will bond to that central atom are called peripheral atoms. And the central atom that we choose usually has the highest bonding capacity. Now, bonding capacity means that it's the number of bonding electrons. So the number of bonding electrons. So if I have an element that has 2 bonding electrons, or 2 electrons that are individual, they're not paired up in an orbital, then that is my bonding capacity. So I start by counting the valence electrons. Sorry, I don't know what's going on here. Counting the valence electrons in the atom by adding the valence in the molecule. This should say molecule. By adding the valence electrons of each atom. Sorry, this should really not say atom, it should say molecule. So if the entity is a polyatomic ion, we add or usually add or subtract the valence electrons to account for the net charge. So if we have additional negative charge, we have to add the same number of electrons to that polyatomic ion. So in this case, I have sulfur and oxygen. So I'm just going to jot these down. Sulfur and oxygen. And I have 3 oxygens. So I have 1 times my sulfur and 3 times my oxygen. And I notice that my sulfur has 6 valence electrons, and my oxygen also has 6 valence electrons. So 3 times 6 is 18 electrons. This gives me a total of 24 electrons that I'm dealing with. So that's an important first step. Okay, I always like to add up my number of electrons And I like to write it out so that I don't make any mistakes. That is super important because it's easy to make some small mistakes in this and it can completely mess you up. So we're dealing with 24 electrons. So I'm just going to write that number down here, 24 electrons. Okay, that's what I get to work with. Make that a little bit better to see. Okay, so then it says arrange the peripheral atom symbols around the central atom symbol and place one pair of valence electrons between each peripheral atom and the central atom to form what we call bond pairs. Now this is a little bit weird and a little bit tricky, so we are going to, in terms of the wording, it's tricky, but really it's a simple concept. So if I write down my central atom, now there's a few ways to determine what my central atom is. The first way is to be based on bonding capacity. However, both sulfur and oxygen have a bonding capacity of 2. But because I have 3 oxygens and only 1 sulfur, sulfur is going to be my central atom, and these 3 oxygens are going to be the atoms that surround that sulfur. So when I go to draw in my peripheral atoms, I am just going to place my peripheral atoms around my central atom symbol, and I'm going to want them to sort of be where my orbitals would exist. So somewhere around that sulfur in one of the 4 sides of our invisible square that surrounds that sulfur. And then what it says is I need to place electron pairs between each of the peripheral atoms and the central atom. So I have to put in electron pairs. So I've put in a total of 6 electrons. Okay, so at this point, I've now used up 6 electrons. So I should probably subtract 6 electrons from my total electrons so that I know how many I have left over to deal with. So now I have 18 electrons remaining that I can kind of play around with. All right, let's take a look at the next step. It says place more pairs of valence electrons or lone pairs all around the peripheral atoms to complete their octet. So let's just see, how did I draw this? Okay. We have our sulfur in the middle. And we have our oxygens around it. And we've added in some bonding electrons in here. Okay, so this is what we have so far. Okay, now again, we have a remaining 18 electrons to deal with. Now this says place pairs of valence electrons as lone pairs. So we have to always place them as pairs. That's very important. Around our peripheral atoms to complete their octets. Now remember, octet means that they want to have 8 electrons surrounding them. So let's just start with our oxygens because they are our peripheral atoms. And I'm going to indicate our lone pairs. They're still electrons, but I'm just going to indicate them with a purple X rather than a dot so that we can see how those are different slightly. They're still electrons though. So I have 1, 2, we'll place them evenly. So 3, 4, 5, 6. Okay, let's keep on going. I've used up 6. Don't know what's happening here. Maybe I should save my font in case it disappears here. So I have 6 that I've used up, 7, 8, 9, 10, 11, 12. So now I've used up 12. I'll keep going. 13, 14, 15, 16, 17, 18 electrons. So what's happened now is I've used up all 18 electrons. I've completely used up my 18 electrons, giving me no electrons to play around with. Okay, so every atom likes to have 8 electrons surrounding it, and now that I've made my peripheral atoms happy, I need to take care of my sulfur atom. Now, if there's any remaining valence electrons, which I have only 0 electrons, so there are no remaining electrons, I place that around my central atom as lone pairs. Now, I simply just don't have those electrons, so still the stage that I'm at right now is I have a diagram that looks something like this. And I have my electrons around each oxygen atom, and our oxygen atoms are pretty happy. They seem to have a full octet, or they seem to have 8 electrons surrounding them. So since I have no electrons left over, I can't do step 4, which is no problem. I can still solve my problem that I have here with my sulfur in the middle not being happy by our next step here. So this says, if the central atom's octet is not complete, we move a lone pair, okay, from the peripheral atom to a new position between the peripheral atom and the central atom. Repeat that until the central atom has a complete octet. So again, let's draw that out. With my oxygens surrounding it, squeeze those in there. I have electrons around all my oxygens. Okay, so essentially what this is saying is that I'm just going to choose an oxygen at random. I missed a couple here. One of the ones that I have bonded, and I'm going to say I'm going to take one of these electron pairs, one of these lone pairs, and I'm going to slide it in between my sulfur and my oxygen. Now, the one thing that is incredibly important to remember when you're creating these structures and diagrams is that these are molecular compounds. They love to share electrons. They're happy to just share with any part of their molecule, so they'll share with any atom that makes up that molecule because sharing is caring, and they're happy to just share those electrons with each other. Now, even when they share, they're both still happy. They are both still happy or full octets. So when we do this, what we see here is we'll get something that looks like this. Okay, let's draw this out now. So we have our sulfur as our central atom still. We have our oxygens. And we still have our electrons, and nothing's changed to these 2 oxygens that are on the left and the bottom here. We still have happy, 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 except what we see here is that we have 2 pairs of electrons. We still have the bonds between our sulfur and our oxygens, but the 2 electrons that were moved and tucked in between the sulfur and the oxygen now exist here in between the sulfur and oxygen. So what that does is we complete an octet. We make everything in this molecule happy. So again, they share electrons. So it doesn't matter that this oxygen has an octet. You can count 18 electrons in that circle that I've drawn. Same with this oxygen, as well as this oxygen. They all have 8 electrons surrounding them. Now when I take a look at sulfur, it kind of will create a little Venn diagram here, and I check it out and I count the electrons. Let me draw that a little bit better. If I count the electrons in that circle there, I will also have 8 electrons surrounding the sulfur, making everything what I like to call happy. And if we're happy, we have a full octet. Okay, so like we see here, everything is happy in our sulfur trioxide as long as we share these electrons that we bumped in from one of our oxygens. Now, it doesn't matter which oxygen you chose to do that. If you chose a different oxygen on the bottom or on the left-hand side, that's no problem. It's all the same. Now, let's just take a look at one little way that this might change. If we have an entity that's a polyatomic ion, we need to just place square brackets around that whole Lewis formula and write the net charge outside of the bracket. So let's take a look at our example with NH4 or ammonium. So with my nitrogen, I have 1 nitrogen and I have 4 hydrogens. So with my one nitrogen, I have 5 electrons. And with my one hydrogen, or my 4 hydrogens, each has 1 electron. So this gives me a total of 5 and 4. Now, because I have a positive charge, it means that I actually had to subtract 1 electron. Okay, because of that, I only have 5 plus 4 minus 1, so that's 9 minus 1, which is 8 electrons. Because of this charge, I have to account for the fact that I've lost 1 electron. Remember, it doesn't mean I've gained a proton. I never can gain protons. I can only lose or gain electrons. So what I have is 8 electrons to deal with. And again, because nitrogen has the best bonding capacity, it will have a bonding capacity of 3. Okay, I know that my hydrogens will be my peripheral atoms and my nitrogen will be my central atom. So I will write out my central atom. And just like with my other examples, I will jot down my elements, my peripheral atoms that surround it. And then what I'll do is I'll place electrons as pairs. Okay, pairs is important, in between my central atom and each peripheral atom to create bonds. So now that I've created bonds, I've used up 2, 4, 6, 8 electrons. So I had 8 electrons to deal with. I used up 8 electrons, which gives me 0 electrons left over, which means that I cannot place any electrons on my central atom, and I have to make sure that my peripheral atoms have a complete octet. Now, the one thing that is a big note that you need to make, hydrogen is happy, okay, I'm going to use my word happy again here, with 2 electrons in its valence shell. Because hydrogen is only in the first row of your periodic table, its octet is 2 electrons. So it is a full octet with 2 electrons, and that's our sort of one example that we have there. Now, again, one thing I need to consider is that my nitrogen has a full octet, which it does. So my nitrogen has a full octet, each hydrogen has a full octet, but because this is a polyatomic ion, I need to note that by placing square brackets around my entire Lewis structure and indicating that this is a positive 1 charge. There was a positive charge or a loss of 1 electron. Now, again, this is super important to have because if we didn't have our positive charge here, this would be a very challenging or impossible Lewis diagram to draw. So by having our positive charge out on the side like that, that makes it a correct Lewis formula. Let's just take a look at some of these examples and we'll take a look at how to draw them and make sure that we are getting through this correctly. And then you'll have some more examples in a worksheet or an assignment that you will have to do following this lesson. So carbon disulfide. Carbon has 4 electrons. Now, if you're not sure where I'm getting these numbers from, I'm getting them from my periodic table, from the column number. Each sulfur has 6 electrons, so that means that there's 12 electrons, giving me a total of 16 electrons to deal with. My central atom is going to be my carbon. Okay, it has a bonding capacity of 4, where sulfur has a bonding capacity of 2. Also, there's 2 sulfurs, which kind of gives me an indication that carbon will be the central atom. Okay, I have 1 body and 4 limbs. That's a way to remember it. I have 1 central atom and 2 peripheral atoms, or however many I might have. So then my 2 sulfurs. And I place those electrons in between there, like so. So at this point, I've started with 16 electrons, but I've used up 4 electrons. So I'm going to subtract 4 electrons, which means I have 12 electrons left to deal with. Okay, I'm going to indicate those with an orange dot, but there are still electrons, don't be confused. Okay, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So I've used up all 12 electrons, meaning that I have no remaining electrons to place on my central atom. Now again, because I need to make sure everything is a full octet, I see sulfur down here has an octet, this sulfur has an octet, but this carbon isn't happy yet. Now because these guys are carrying molecules, this guy is going to share his electrons, and this guy is going to share his electrons. So what happens is I'll draw it on the side here. I get my carbon, my sulfurs, and I get my electrons that were initially in there, and then these two pairs kind of shift around, these two pairs kind of shift around, and I get these two that get moved right into the middle, creating a double bond in between our carbon and our sulfur. Now when I check this out, I see that every atom has a complete octet. So that is done. Okay, let's look at our next example, phosphine. Okay, or phosphine. Phosphorus has 5 electrons. Hydrogen each has 1 electron, each has 3. So a total of 8 electrons. When I start by drawing my central atom, again, 1 central body, 3 limbs. So I have phosphorus with my 3 hydrogen, okay, and I place my electrons into those bonds there. So now I've used up 6 electrons, giving me 2 electrons left over to place. Now I check to see if everything in my peripheral atoms has a complete octet. Now remember, hydrogen is that special one. It's happy with 2 electrons in its octet. So that is in fact done. So then I have 2 remaining electrons left behind that I can actually place just on my central atom like so. So when I do a check at the end, all my central atom and each hydrogen has a full complete octet. I've used up all my electrons, giving me no electrons left behind. This is my complete diagram. Okay, let's take a look at hydrogen sulfide. Each hydrogen has 1. There's 2 of them, that's 2 electrons. Sulfur has 6 electrons, giving me another total of 8 electrons. Again, sulfur is more than likely going to be my central atom. I have 1 sulfur, I have 2 hydrogens, 1 body, 2 arms. So I draw out my sulfur, add my hydrogens, place 2 electrons in between each peripheral atom as a pair. So I've used up 4 electrons there, giving me 4 electrons left behind. And I place then my remaining electrons on my peripheral atoms. However, in this case, my peripheral atoms are happy with 2. So I place my other pairs on my central atom until it has a complete octet. I've used up 4 electrons, meaning that I have none left behind, which gives me this as my Lewis diagram for hydrogen sulfide. Now if I check out my hydrogen or my hydroxide ion here, again, let's take a look at the number of electrons. I'm going to have to do this kind of on the side here because I'm running out of space. But my oxygen has 6 electrons. My hydrogen has 1 electron, but I have 1 extra electron there. So this gives me a total of 8 electrons again. Now, again, I've added in that extra electron because I have a 1 negative charge. If I had a 2 negative charge, I was adding 2 electrons. So let's start out. I would say that, again, oxygen will be my central atom because it has a bonding capacity of 2, whereas hydrogen has a bonding capacity of 1. So that will be considered my central atom. Now I'll place my hydrogen beside it, and I will place my bonding pair in between my hydrogen and my oxygen. I've used up 2 electrons. I have 6 left behind. I'm going to squish that in here. So I have 1, 2, 3, 4, 5, 6 electrons, meaning I've used up all remaining electrons. Now the last step here is, because this is a polyatomic ion, I need to be sure to put square brackets around my polyatomic ion with the charge outside of that. Again, I have a complete octet. Hydrogen's happy with 2, oxygen's happy with 8. I put my square brackets and my negative charge on the outside. being the appropriate Lewis structure for my polyatomic ion. Now, this is the end of determining our Lewis structures. Again, notice that if we have two pairs of electrons in between our central atom and our peripheral atom, it means that this is equal to a double bond. If you were to have three pairs, it would mean that you have a triple bond. And again, that doesn't really change that much of our Lewis diagram. This would just make this a little bit different of a bond, but it doesn't really change a lot in terms of the shape or anything of this molecule. So that is part of it. And just remember that these guys are happy to share. They think sharing is caring, and sharing is important between these atoms to complete all atoms' octet in the molecule. So you should be able to move on, and there's going to be an assignment on these Lewis structures. So good luck.